Hi guys, so we have heard of the powerful concepts change of probability measure, Radon-Nikodym derivative, risk-neutral valuation, etc. We know that these concepts are extremely simple and interlinked, but are usually presented in abstract terms, which might create the impression that these are complicated theoretical concepts, but they aren't. The reason these concepts are presented in abstract terms is because they apply across settings, single period, multi-period, discrete time and continuous time, and they retain the same interpretation across settings, so it's tempting to generalize them really quickly, and that's what happens. But this generalization can lead to the loss of intuition, so the purpose of this video is to introduce these concepts in simple settings. If you don't get distracted by some technical conditions that are needed when dealing with continuous time in more general settings, and focus on the parallels instead, then you will see what we learn in the simple world applies in the more advanced settings, and the gut feelings will then begin to work. So let's go to casino to lose some money, call it the price for entertainment. No place like the roulette table. This is the European version with 37 pockets numbered from 0 to 36. There are versions with 00 and 000, but let's create our own version with fewer pockets and exaggerated profits so that the numbers and results are easy to see. So let's reduce the number of segments, meaning the size of the individual segments increases. Let's stop at 7, which is what we can manage on the screen. Let's number the pockets from 0 to 6. There are 7 segments of equal size, so assuming no cheating, we shall expect the probability of the ball falling into one of the pockets to be equal to 1 divided by 7, and same goes for the other segments. Now, if we place a bet of 1 quid on one of the numbers, the casino will give us odds of 5 to 1, meaning if the ball comes to rest on this number, we will win 5, and if it doesn't, then we lose 1. We can say our profit and loss is a random variable which takes two values, 5 and minus 1. We know the probability of us winning 5 quid is 1 divided by 7, because we get 5 only if the ball lands in the pocket we have placed a bet on. We will lose 1 quid if the ball lands in any of the other 6 pockets. So the probability of losing 1 quid is 6 divided by 7. We can calculate the expected profit and loss, which is just the value times the probability summed across all possible values. This is now just 5 minus 6 divided by 7, or minus 1 divided by 7. So on average, every time we play this bet, we lose a seventh. Some of it goes to cover the cost of casino, some to their shareholders, some to other causes, who knows. In addition to placing bets on a single number, we can also place bets on combinations. For example, we can place a bet on the ball landing in one of the red pockets. The odds would be 1-1, meaning we get 1 if the ball lands on one of the red segments and minus 1 otherwise. We can assign probabilities to these values, as the probability of each segment is 1 divided by 7, and there are 3 red segments. The probability of red is 3 divided by 7. The probability of non-red, which is black plus green, is then 4 divided by 7, and we can calculate the expected value of our P&L, which is value times probability. This is 3 minus 4 divided by 7, so again we lose 1/7 on average. So we have a probability model for the wheel, and as you would know, one represents the probability using the tribe in terms of sample space, sigma algebra of subsets of this sample space, and a probability measure. So omega is the sample space of outcomes, which is the set of the 7 numbers here. F is the sigma algebra and represents the different types of events one might be interested in assigning probabilities to. For example, one might want to bet on a single number, pair of numbers, odd numbers, numbers lower than 3. For this simple experiment, we have a finite number of outcomes, so we can easily generate the power set, which will cover all combination of events one might be interested in. This is because by definition the power set contains all subsets of the set, including the empty set and the whole set itself. Just to refresh memory, power set will include the empty set because empty set is a subset of every set. The set comprising the individual numbers, set comprising all possible pairs of numbers, set comprising all possible combination of 3 numbers, and so forth until the set comprising all of the 7 numbers. The total number of subsets in the power set comes to 2 to the power number of elements, which is 128. We can assign probabilities to these subsets and we will be able to cover all events that may be of interest, but it's an overkill for the simple case we have here. All we need to know is whether the number is red. The sigma algebra one needs, or shall we say, the sigma algebra this random variable generates is rather simple. Red event, which is when the variable takes value of 1, consists of the pockets 4, 5 and 6, and its complement is then the remaining pockets, and we have to include the impossible event and the certain event. And now if you look up the definition of sigma algebra, you will see this set of sets satisfies the criteria listed in the definition of sigma algebra, and you can easily see this set covers the type of events we would be interested in as far as the game of red versus non-red is concerned. One can complicate the structure of this set to cover other types of games one can play, but that's a topic for another day. Here we just mentioned this so that you get the idea that the same kind of structure works across settings, only the details vary. Now we can ignore the sigma algebra and focus on the values the random variable take, which is we either win 1 or lose 1. The game is biased against us. We can play same strategy on the black pockets and we will see that we lose 1/7 on average every time we play. The source of the bias is easy to link to the green pocket, and the reason for the bias is obvious. Casino has to cover the cost and make profit for the owners. If we were to go to another casino, they will give us more or less the same odds, so we might as well accept the price and carry on. But even then, we would like to dig a bit deeper to devise alternative ways of doing calculations, so let's dive in. Hypothetically, if we were to turn the game into our favor, or say into a fair game, there are at least 3 ways we can do so. We can ask the casino to change the random variable, which is the odds. This can happen in 2 ways. Increase the odds so that we get more than 1 when our color turns up, or we can ask for the green segment to be removed and split between red and black. Each subsegment will then take half of the probability mass of this segment, and obviously the probability of the ball landing in the red pockets increases by 0.5 divided by 7. Both of these approaches amount to changing the random variable. Remember, random variable is a mapping of the events to the real number. In the first approach, we are changing the values the random variable takes. In the second approach, we are mapping more events to the profit scenario. And the third way, which is the topic of this video, would be to leave the random variable as it is and alter the probability. Say we change the mechanism by using some magnets to increase the probability of the balls landing in the pockets we are betting on, say the red segments. And let's represent the new probability measure by Q. Q comes after P, so we just choose the next alphabet. And for the game to be fair, we know the probability of us winning should be 3.5 divided by 7, which is the same probability of us losing 1 quid, so the two will balance each other. Now if we calculate the expected value under this new probability measure, which is value times probability, then no surprise we get 0. Notice we represented the expected value under the measure Q with tilde E. Let's put the two probabilities side by side. Now let's create a new variable Z as the ratio of the two probabilities. So we just take Q and multiply it by the inverse of P. The 7's cancel and we get 3.5 divided by 3. Doing the same for the second row and cancelling 7's again, we get 3.5 divided by 4. So getting Z is easy peasy, but this Z is one of the most important thing, the Radon-Nikodym derivative. Here in the discrete case, it's just the ratio of the two probability masses. But if you start thinking of generalizing along the lines of going from discrete to real numbers, then you will naturally think of calculating this ratio in terms of infinitesimals. So dq divided by dp, which is then like the derivative of q with respect to p, derivative of one probability measure with respect to another. But let's not go there. Let's verify some properties of this Radon-Nikodym derivative. Let's start with the expected value under the p probability measure. So we take the values and multiply them by their probabilities. The 3's and 4's cancel and we get half plus half, which is 1. So the expected value of z with respect to probability measure p is equal to 1. We also see this z got to be positive because it's ratio of two probabilities. So can we say z is a density then? Well, it is positive and sums to 1, so nothing wrong with calling it a density. For the second important property, let's try another random variable. Say the casino is running a promotion, so if red turns up, it gives us 2 quid. Call it happy hours. Let's calculate the expected value of this random variable under the 2 measure. Let's start with the tilde version, which is the measure q. Value times probabilities. 2 minus 1 equals 1. So it's just 3.5 divided by 7. So we on average earn half a quid. Now let's try the expected value with respect to measure p. Values times probabilities again, but now the probabilities are the p probabilities. 6 minus 4 equals 2. So under this measure, we earn a bit less as one would expect. You got to ask, what's the relationship between the two expected values, or how are the two expected values linked? To see, let's create a new variable as x times z. So we multiply x by the Radon-Nikodym derivative, and then expected value is just values of this expression times the probabilities. The 3's and 4's cancel, and 2 minus 1 equals 1. So we get 3.5 divided by 7, which is exactly the expected value of x under measure q that we saw before. So we can see the expected value of x times z under the probability measure p is equal to expected value of x under the measure q. And by the way, it's easy to verify this relationship algebraically because z is q divided by p, and expected value means we multiply it by p, so the p's cancel, and we then have values times probability under q, which is precisely the definition of expected value under q. Now can you verify that this same relationship works for the random variable y? This result looks very simple, but it's a very powerful concept that generalizes across settings and will help us simplify complicated problems when we move to continuous time. Now you can ask, say I have been given a random variable in a probability measure. Can I determine a new probability measure such that the random variable has some given expected value under the new measure? And this two states world is relatively easy. Say we start with this biased casino game where we lose a 7th on average, and we want to determine another probability measure which will turn the game into our favor. Say we earn 1/7 on average instead. Let's represent the probability of the random variable taking value 1 by p and the probability of -1 by q. Dividing these symbolic probabilities under the q measure by the probabilities under the p measure will give us z, the Radon-Nikodym derivative. Now to determine the two variables p and q, we need two equations. For the first, we can make use of the properties of z, which is expected value of z, values times probabilities under p measure. But the values contain p and q now. The fractions cancel each other and we get p plus q. We know the expected value of z equals 1, so we get the obvious result that the sum of the two probabilities should equal 1. For the second equation that we need, let's make use of the given condition, which is the expected value under the measure q must equal 1 divided by 7. The random variable takes values 1 and -1 with probabilities p and q respectively, so p minus q must equal 1 divided by 7. We have two equations and two unknowns, and if you solve these equations, you will get p equals 4 divided by 7 and q equals 3 divided by 7. We can substitute these values of p and q to get the values of z corresponding to the two values that the random variable takes. Substituting for p and then cancelling 7's, we get 4 divided by 3. Similarly, substituting for q and cancelling 7s, we get 3 divided by 4. So z, which is the Radon-Nikodym derivative, takes values of 4 divided by 3 and 3 divided by 4. So we have determined the probability measure which will achieve the desired objective. Let's quickly verify that it indeed does achieve the objective. Let's start with the expected value under q, values of the random variable times the respective probabilities. 4 minus 3 equals 1. So we get 1 divided by 7 as required. Now under this probability measure, we are making money on average. We can also verify that the Radon-Nikodym has the desired properties. Let's start with its expected value under the measure p, values of z times the respective probabilities. The 3's and 4 cancels, and then 3 plus 4 equals 7, so we get 1, which is what we expect to see. Now as an exercise, can you verify that the expected value of y under measure q equals the expected value of y times z under the measure p? Now this casino game is not much different from what happens when you invest in a financial asset. It's just that you pay your maximum loss upfront here, but we normally view a financial investment in terms of the price and payoff. If this casino game were to be structured like a financial asset, then you can view the 1 quid you paid as a price. You paid this 1 quid irrespective of the scenario, so you can increase the profit and loss by 1 to get the payoff. Now if red turns up, you get 2, and if red doesn't turn up, then you get 0. So 1 quid is the price, and random variable which takes values of 2 and 0 is the payoff at maturity. So we can apply the same concepts to financial assets. Let's increase the complexity a bit by switching to betting on individual pockets. So we have the 7 numbers, and hence the sample space now consists of 7 points. Call these the possible states, and let's represent them by W. The probability of each pocket is 1 divided by 7, and we know that they will probably give us odds of 5 to 1. So the ball can come to rest on one of the pockets. We can represent our profit and loss by a random variable, which maps these 7 outcomes to numbers. Let's say we place a bet of 1 on the number 6. So if 6 doesn't turn up, we lose 1 quid, and if the ball comes to rest on 6, then we get 5. Let's add this 1 quid we put on the table to the random variable under all scenarios, because we paid this 1 quid upfront and we represent the resulting random variable by x. So we will get 0 back if the number 6 doesn't turn up, but if it does, then we get 6 quid. And we paid a price of 1 quid for a claim to this payoff. In a way, a payoff of 6 under state 6 cost 1 quid. It's best to standardize the payoff to 1 quid, and we can do so by dividing the price and the payoff by 6. The security now pays 1 quid if the state happens to be number 6 and 0 otherwise, and cost 1 divided by 6, which we represent by V. The subscript serves as the indicator of the state under which it pays 1 quid. As you may recall, a security that pays 1 quid if a state occurs and nothing otherwise is called arrow-debreu security. It's a concept of fundamental importance in financial economics and goes by several names like pure security, etc. Similarly, we can consider a bet of 1 quid on another number, say the pocket numbered 5. So now we will get 6 if the state 5 occurs and 0 otherwise. Dividing by 6, we get the price of the arrow-debreu security corresponding to this state. We can apply the same procedure to the other states, and we will see the price of a security paying 1 quid is 1 divided by 6 for all states. And don't forget, Vi represents the price of the security that pays 1 quid if state I happens and 0 otherwise. So we have a vector of state prices, and this vector is called state price vector. No surprise there. I agree with you, this is too easy, so let's complicate things a bit. Let's say the casino is paying different odds on pockets of different colors. Say it's running a promotion on the red color. We already know the state price of the states with odds of 5 to 1 is 1 divided by 6. It's easy to deduce that the price of the states with odds of 4 to 1 will then be 1 divided by 5, and the price of the states with odds of 8 to 1 will come out to be 1 divided by 9. To avoid any ambiguity, let's write the state prices against the individual states. Now let's say we have a more complicated asset that pays different amounts in the different states or pays something in more than one state. Can we calculate the price of such assets? It's easy matter. If we know the prices of arrow-to-brew securities for all states, we just multiply the payoff in each state by the respective AD price and sum across states. This is all nice and simple, but it's better to write it in terms of expectation so that we can generalize the result. Let's say PIs represent the probabilities of the states. They can be arbitrary probabilities, say your personal beliefs. Doesn't matter where they come from, as long as they are positive and sum to 1, we are good. Also, the probability of some of these joint events equals the sum of their individual probabilities, which is also obvious to verify. Let's multiply and divide it by PI. Let's represent the ratio of arrow-to-brew price and the probability by M. If we substitute this M for price divided by P, we can then write the price as expected value. This M is like a stochastic discount factor. And this stochastic discount factor, which goes by several names like the pricing kernel, is nothing but the price of the state per unit probability. In a way, how much are you paying for a state per unit probability? And we can also say then the state price is equal to the probability of the state times the discount factor. You would have thought that the high probability events would be more expensive than low probability events, but apparently not. States with higher values of M are in high demand because people are willing to pay more for such states per unit probability. Let's apply this to the example we have. Let's say we don't think any state is more likely, so we say the probability of each state is equal to 1 divided by 7. M is then AD price, which we have represented by V divided by probability. You can see the discount factors for the green and black states are greater than 1, and the discount factor for the red states are lower than 1. Payoff in the green state is valued more. Reason being, casinos doesn't pay much when this state occurs because the odds are the lowest, so payoff is more desirable. When red state occurs, casino pays a lot, so money in these states is cheap. And financial markets, securities that pay more when the state of the economy is bad are generally in high demand. Right, so what's the price of a risk-free security? A risk-free security here means a security that pays the same amount irrespective of the state. So let's price a security that pays 1 in all states. We just replace Xi's by 1. So it's just the sum of AD prices, which is column V. By the way, AD prices means the arrow-to-brew prices. If you sum these, you will get 31 divided by 30. So you're paying a bit over 1 quid to get 1 quid. This is because this casino game, despite the generosity of its management in the red states, is biased against us if we don't stick to red. So by playing, we're losing money. Think of this as the negative interest rate environment, and this D is pretty much the risk-free zero coupon bond. Now let's try a different approach to calculate the price. Take the price of the pair of X as Xi times AD prices summed across states, and now divide and multiply by D instead. Remember, D is the price of the risk-free security. This V divided by D, which we can represent by Q, are not probabilities but can be interpreted as such. They're positive, and remember, D is the sum of the V's, so they sum to 1. So for all practical purposes, they are probabilities. And if we make the substitution, we can then write X times Q as expected value. We use tilde for expectation with respect to the Q probabilities. And what we have now is nothing but the risk-neutral valuation formula, with Q as the risk-neutral probabilities and D, which is the price of a zero coupon bond, as the discount factor. This D represents the amount one needs to invest today in order to get 1 quid at the maturity. Its inverse, which is 1 divided by D, then represents the forward value of today's 1 quid. So these risk-neutral probabilities are just forward prices of the states. Can't get any easier than that. Now let's calculate the risk-neutral probabilities for the example we have. The values of AD prices are in the column V, and we know d is equal to 31 divided by 30, so we just multiply v by 30 divided by 31. We could further simplify some of the fractions, but it's better to keep the same denominator, so this is why you see 93, so that we can easily compare. If you sum the ratios, you will get 1, easy to check, starting at the bottom. 10 times 3 is 30, 15 times 3 is 45, and 30 plus 45 is 75, 75 plus 18 is 93, and then 93 divided by 93 is equal to 1. So KYs are indeed positive and sum to 1, so they are indeed probabilities. If you redraw the size of the segments using these probabilities, you can see the green and black segments are relatively much bigger. So by giving generous odds on the red segments, this casino is making them cheap, and you can see the risk neutral probabilities extract the information from the prices and make it easy to value other cash flows. Now, a question for you. What's the relationship between the Radon-Nikodym derivative and the stochastic discount factor? This how is Z related to M? Is one just the forward value of the other? I will leave you to figure it out, and I will conclude by saying that this simple approach can be easily generalized to multi-periods. Say you're playing multiple rounds. The concepts we discussed, such as Radon-Nikodym derivative, risk-neutral valuations, etc., carry the same interpretation, just the details of the probability space change. And multi-periods one also sees some martingale properties which are very useful, but again quite intuitive. One can also easily generalize the approach to continuous time. As we mentioned at the beginning, in continuous time, things might look slightly complicated because one needs to introduce some technical regularity conditions. But if you focus on the parallels and don't let the technical conditions confuse you, then it's all very easy. Please give a thumbs up if you would like to see similar videos, and I look forward to seeing you in the next.